Okay, so now we're going to solve problems with gases, and we need to use stoichiometry, but the problem is now we are not at STP. And so if we're not at STP, we cannot use this number, the 22.4 liters per mole. We can't use that because we are not at STP. So we have to use a combination of stoichiometry and the ideal gas law when solving problems where we are not at STP. So let's go through a couple problems together, a couple of different types of problems. And so our first one is, what mass of silver oxide is required to form 388 milliliters of oxygen gas at 734 torr and 298 Kelvin? So we have an equation here. So first of all, let's go ahead and balance this equation. So here I have two oxygens, but in the reactants I only have one, and so we're going to need to double silver oxide. And so this is going to be a 1, and then here you can see I've got 2 times 2. I have 4 silvers, and so this is going to need to be a 4. All right, so now that the equation is balanced, our coefficients are 2, 4, 1. Let's digest the problem a little bit. It doesn't look like it's a very big problem. It's one short sentence or one short question, but we actually have a lot to do in this problem. So what variables do we know? We know that we want to make 388 milliliters of oxygen gas. And milliliters, to get 2 liters, because we can't use milliliters, we need to divide by 1,000 milliliters and multiply by a liter. So that's going to be equal to 0.388 liters of oxygen. So I know that my volume, and that's going to be 0.388 liters, and that's oxygen. So that is not silver oxide. That is specifically oxygen. I know that the pressure, and we don't need to put V2 there. We just put V. V of O2. That's really what I should put. V of O2 on the bottom here. We know that the pressure is 734 torr. And we also know that the temperature is 298 Kelvin. Okay. Excuse me. What are we trying to find? It asks us what mass of silver oxide. So we are trying to find the mass of Ag2O is what we're trying to find. We don't know that. Excuse me. So we're going to make a plan. How can we go from oxygen? We know that we're going to form 388 milliliters or 0.388 liters of oxygen. How can we go from that to silver oxide, the mass of silver oxide? Well, if we use the ideal gas law, remember that we are not at STP, okay? So we cannot use 22.4. So first step is we need the moles of oxygen. How many moles of oxygen are we going to form? Because we can never compare substances unless we're in moles. So when in doubt, go to moles for anything. So our first step is we're going to use the ideal gas law to find N of O2. We need the moles of O2 is what we're going to solve for. And then once we have that, then we can just use regular stoichiometry. We can go from moles of O2 to grams of silver oxide with stoichiometry, with the train tracks. So this up here, step 1 is PV equals nRT. Okay, so we have to do this in 2 different steps because we're not at STP. So our first step, PV equals nRT. So PV in RT for step 1. Pressure we know is 734 torr. The volume is 0.388 liters. And remember, this is for oxygen. We're going to solve for moles of oxygen. We'll come back to the R value in a second. And temperature is 298 Kelvin. All right, R value. Our pressure is not in atmospheres. So you can do 2 things. You can convert pressure to atmospheres. Or if you scroll back up to the top, I gave you... If you scroll back up in your notes, I gave you 3 different R values. One of them has torr in it. So you can just use the R value of 62.4 because our pressure is in torr. If you would prefer to use this R value, you're going to have to convert your pressure from torr to atmosphere, which means you just need to divide it by 760. But I'm just going to go ahead and use this R value, 62.4, because my pressure's in torr. 62.4. All right, so we can go and set that up and solve for N. So N is going to be equal to, we're going to divide by RT to get N by itself. So pressure times volume over R times T. So N is going to be equal to 734 times 0.388 divided by 62.4 times 298. So that should give us 0.0153 moles. And remember that this was for oxygen. Okay, so now we're going to go from moles of oxygen to grams of silver oxide. You can use your foldable or your chart, whatever works better for you. But we're going to set up train tracks. And this is going to be our starting number. Moles of O2. So 0.0153. The mole ratio is the next conversion factor, which means that we need to use our coefficients from our equation. Oxygen is going to go down here, and that is 1 mole of oxygen on the bottom. And we are trying to find out, about silver oxide. So that's this substance here, not silver, silver oxide. So we have 2 moles of silver oxide. And then because we're going to the mass, we want to know about the mass, we're going to need the molar mass of silver oxide. So if you look up silver on the periodic table, you're going to have to double that mass and then add it to 16. Silver oxide only has 1 oxygen and it has 2 silvers. So find those numbers, add them up. Over here, we should put mole on the bottom. And remember that molar mass is grams of 1 mole of substance. So Ag2 on the bottom, 1 mole of that. And then the molar mass, you should get 231.74 grams of Ag2O. And then we're going to type that all in. Remember that when you type these in, you're going to multiply across the top, divide on the bottom. What's nice about this one is that both of the numbers on the bottom are 1. And so you should end up with 7.10 grams of silver oxide. And so if you are starting out with information about the gas, then you're going to have to solve ideal gas law to find the moles. And then you're going to have to do stoichiometry to find out about the other substance that's not a gas. Or sometimes it is a gas too. Maybe they want to know particles or grams or the volume of the other gas. And you can solve this as well. But if you're not at STP, you cannot use the 22.4 liter shortcut. in the train tracks. You have to solve it with the ideal gas law. Okay, example 2. So this way is going to be a little different. We are going to know the mass of something. We're going to have to do stoichiometry as our first step, and then we're going to have to solve ideal gas law as our second step. So it's going to be a little bit of a reverse from what we did in our first example. So 62.7 grams of nitrogen gas and excess oxygen react. When you see excess, you can ignore that. They generate nitrogen dioxide. When it says excess, it just means that there's enough oxygen to react. There's plenty of oxygen available. It's not going to affect our calculation. So we don't care about excess reactants. Okay. If the NO2 is at 352 degrees Celsius, right off the bat, we know that we can't use Celsius, so we're going to add 273, and that is 625 Kelvin. It is at 0.724 atmospheres. What volume will it occupy in those conditions? Okay, first let's balance this equation. Over here I have 1 N, here I have 2 N, so I'm going to need to double this so that I can have 2 N's on the right side. And now I have 4 oxygens. 2 times 2 is 4, and so I need to make this reflect that. If I do 2 times 2, this will also be 4. And so N2 is just going to have a coefficient of 1. So 1, 2, 2 is the balanced equation. All right, what variables do we know? We know the mass of nitrogen gas. So remember that nitrogen gas, it's diatomic, so it's N2. We know that the mass is 62.7 grams from the problem. We know that the NO2, the temperature of NO2 is 625 Kelvin. We know the pressure of NO2 is 0.724 atmospheres. It wants to know what volume will the NO2 occupy. So we are trying to find the volume of NO2. That's what we're trying to find. Okay, so our first step is we cannot use grams of nitrogen. We always have to go to moles. Okay, and we can use stoichiometry to go to moles by using the molar mass, and then we can go to moles of NO2 by using our balanced equation. So our first step is, notice we're not at STP. We are not at standard temperature. We are not at standard pressure. So again, we cannot use 22.4. We are not at STP. So our first step is we're going to go from moles, we're going to go from grams of N2, that was our given, and we're going to go to moles of NO2 using stoichiometry. So using your foldable or your mole map or whatever you're comfortable using. And then now that we have our moles of NO2, we can find the volume of NO2 using the ideal gas law. Because they gave us the pressure, they gave us the temperature, we're going to have the moles from step 1. Look up the R value, and we're going to solve for V. Okay, so let's go ahead and try to plan that out here, work that out here, solve it. All right, so step 1, we said we're going to need to do stoichiometry, so we're going to need train tracks. We're going to start with 62.7 grams of nitrogen. To go to moles, we need the molar mass. Remember that this is N2. So you're going to take the mass from the periodic table is 14.01. You're going to double that. So it should be 28.02 grams of N2, and that goes on the bottom so that our units can cancel. And that's grams per mole, so this is 1 mole of N2. Our next step is the coefficients, the mole ratio from our balanced equation. N2 is 1, and NO2, what we're trying to find, is 2. So N2 needs to go on the bottom because remember that our units need to cancel. So 1 mole of N2, and that's going to go with 2 moles of NO2. And then we're going to stop there because we can't use 22.4 for the volume. Let me erase this. We don't need this part, and actually we don't need that either. We're going to be done with the stoichiometry. That should be, let's see, multiply the top, divide by the bottom, 4.48 moles of nitrogen dioxide. So now we can take that number and plug it in with the rest of the numbers from the equation, from the question that we didn't use, and solve PV equals nRT. Okay, so let me move this up just a little bit. Okay, pressure, volume, moles, R, and temperature. The pressure was 0.724 atm. And again, this is for NO2. The volume is what we're trying to find. Moles was 4.48. The R value, we are in ATM now, pressure. So our R value is the 0.0821 number because that was the number that has pressure in atmospheres. And then the temperature is 625 Kelvin. So we're going to go ahead and solve for V. PV equals nRT. To get volume by itself, we're going to divide by the pressure on both sides. So V is going to be equal to nRT over the pressure. And we're going to go ahead and plug those numbers in and solve. So 4.48 from our part 1 answer is the moles, 0.0821 is our R value, the temperature is 625 Kelvin, and we're going to divide by 0.724 atmospheres. And you should get a volume of 317 liters of NO2. And they didn't specify if they wanted the volume in milliliters or liters, so you can just leave it in liters. That should be your answer. So notice here, in this problem, we had to do stoichiometry first to get the moles of the substance, and then we were able to solve that with the ideal gas law. So a little bit different order than what we did with our first example up above, where we solved ideal gas law first to get the moles, and then we used the moles to do stoichiometry to get the mass of the other substance. So when you're solving these problems, it's usually one of two ways. You either doing ideal gas law first to find moles and then using stoich train tracks, or you're doing stoichiometry first and then you're solving the ideal gas law.